Okay, now what we're really interested in talking about are topographic maps. That's really the chutzpah of today's talk. Chutzpah, I think that's a Hebrew word, and today's the first day of Hanukkah. Okay, so in a topographic map, basically what's going on is it's a regular map view of a place, but you've got lots of lines and loops drawn on it that show areas of constant elevation. It's a way to show a three-dimensional map on a flat two-dimensional piece of paper. And like I said, the way you do that is with lines that show areas of constant elevation. So in topographic maps, and I'll draw a picture of this to kind of give you an idea more of what it looks like. The lines show region of the same elevation. Show, S-H-O-W. Lines show regions of constant elevation. Therefore, we've got some things that follow as a logical consequence of lines showing constant elevation. Therefore, the lines cannot cross. If the lines crossed, that means at the same spot of ground is at like two different elevations. So it's like this area of floor is at 2 feet and it's at 12 feet, both at the same time. You go figure it out. No, it's not possible. It's physically impossible for topographic lines to cross. Also, all lines must eventually meet, assuming the map's big enough. Eventually meet. Okay, so let me draw a picture of what I'm talking about here. I'm going to draw a side view first. So let's say that we're looking at some area of ground, and there's a pond right here, and the ground's kind of bumpy, and then we've got like this mountain over here. Okay? If I were to draw topographic lines on this, so let me just, here's a person. Hello. Here's a tree. And it's Christmas time almost, so we've got a star on top. Yeah, I can't draw a star. So topographic lines of constant elevation might be look something like this on a side view of a map. Now normally on maps like this you don't draw topographic lines. I'm just trying to show you what we would have if we drew lines of constant elevation. If you were to walk around this hill at this line, you'd stay at the same elevation. Similarly, at this pond here, we've got lines of constant elevation, topographic lines, or contour lines. All right, so now if we were to take this and we were to rotate it so that we're now looking at it from the top, we might see something like this. Let me draw a big rectangle. I should extend it all the way. So our mountain or our hill right here, we might see looking kind of like this. Where now these lines, these circles that I'm drawing are contour lines. If you were to walk, say this contour line right here, maybe is the same thing as this contour line right here. Same line. If you were to walk around that line, you'd stay at the same elevation all the way around the hill. Similarly, we've got a pond over here. And you've also got contour lines going down. Although the difference, though, is that this is going into the board. This is negative. This is where we've got water ponded. And this is popping out at you. It's got that 3D effect. But they both show areas of constant elevation. Now, in the areas between here, we might have contour lines that maybe kind of look like this or something. Okay, so here's just some terms you need to know for doing the assignment. Relief. That's all that is the high point on the map. It's a simple map. High point minus the low point. And that equals relief. So, if in our hill with the pond analogy, the relief would be the top of the hill minus the bottom of the pond, and what's that distance between them? It's just saying the maximum change in elevation that you have on the map. And this is going to be in feet or meters, depending on the map, feet or meters. Now there's something called the contour interval. Contour interval. And that is the vertical distance between contour lines. The vertical distance between contour lines. And this number is given to you. I gotta wiggle the mouse here because my computer's going to sleep. This is a number given on the map, in the key or the legend of the map. Okay, so going back to our contour map example here. This is just some map here. Now, so the contour interval, that's like, say it's 10 feet. Here's the key of my map. Contour interval is 10 feet. So that means between this line and that line, I'm changing in elevation 10 feet, and between this line and that line, I'm changing an elevation of 10 feet. Now, what would it mean if my lines and my contour lines are really super duper close together? What would that mean, say, in terms of how easy it is to hike? Well, if they're really close together, that means that over a short horizontal distance, I'm going up or down 10 feet. So I'm going up 10 feet really fast. That means if the lines are really close together, that means it's a really steep hill that I'm on. Conversely, if my lines are really far apart, and that's 10 feet, I've got to walk a long ways before I've gone up or down 10 feet. So you can tell steepness by the contour lines. Now, I want to get back to something I talked about earlier. What would happen if contour lines crossed? What would it mean if I had this going on? Look at these points right here. Bah and bah. How could those 2 points be at 2 different heights? They can't. Impossible. Now, your lab is going to ask you about how you can identify an angular unconformity in map view. Now, remember, an angular unconformity in side view looks like that. But what would that look like in map view? Well, your lab, I'm looking on the second page here, I'm going to draw this. Your lab draws this like this, basically. We'll make this type of rock the swirly rock. Now, so we've got these 2 stripes going like this, and we've got some other rock contact here. Wherever you see one type of rock overlying another kind of rock, or multiple kinds of rock, what that looks like is something like this. So you've got your tilted beds here, and these tilted beds are the same as these beds right here. So we've got dots, and stripes, and more dots, and more stripes. And we've got some other rock contact laying on top of it. This is the swirly rock. And over here there's either non-deposition, that's why there's none of the swirly rock, or it could have been from erosion. But I want you to see how an angular unconformity looks in map view and how we're used to it looking like in the side view. Okay, and at this point you should be ready to go on the lab. We're going to be looking at the Grand Canyon, and hopefully we'll get it done. So, thanks for watching.